All right, so here is geometric. I'm going to try and do this one a little bit quicker, kind of keep the pace up, but similar stuff going on here. The big difference with geometric sequences is that we're not adding a constant difference, we're multiplying by a constant, what we call a ratio. So we multiply by r is typically the letter that we use there. So we're multiplying by r to get from the first term to the second term. We're multiplying by that same r to get from the second to the third, and multiplying by another r to get from the third to the fourth, and so on. So if we had this, we define our first term as just a, kind of like we did on the other sheet. Our second term would be a times r. Our third term would be a times another r, so a times r. The nice way of writing that is r squared, and multiplying by a third r for my fourth term, so a times r times r times r, also known as r cubed. All right, so that is our pattern that we're going to do in a geometric sequence. So if I look down here, the ratio that we're multiplying by, I'm not just looking at a difference, and we're looking at a ratio. So what did I multiply by to get from 3 to 6, right? And you can do 6 divided by 3 to get 2. 2 is that ratio. So we multiplied times 2. And to get from 6 to 12, it was times 2. And from 12 to 24, we're doing times 2. All right, and so we could think of this as 3, and not times any 2's. And then when this was, my second term was 3 times 2, and my third term was 3 times 2 2's, which is 2 squared. And my fourth term was 3 times 3 2's. Fourth term was just 3 2's, and that'll come back in our explicit formula. All right, so that's the geometric pattern. The recursive formula, so I need to define it in terms of the previous term, right? That's our recursive definition. So sorry, I went with the subscript there. I'll turn that into parentheses. A of n is equal to a of n minus 1, and then instead of before, we were adding a constant difference. We were adding d every time. Here, the big difference is we're multiplying by r. We're multiplying by a ratio. We're multiplying by the same number over and over and over again. And I should point out that it's not just adding a difference here with arithmetic. You could subtract a difference as well. We could think of it as just plus a negative, and in fact I did that here with this -5 where we were going down. We're actually subtracting 5 every time. And the same thing here, multiplying by a ratio. Well, we can easily make that division by multiplying by a fraction. Multiply by 1/2. I'll do that down here. So this covers addition, subtraction, multiplication, and division, actually, even though we just think about it in terms of addition and multiplication. So we're multiplying by that ratio, but I always need the previous term, so I need some starting point for this to be well defined. I've kind of defined the pattern, but I haven't well defined the entire sequence. I need to know what my first term is, and so a of 1 is, and in this case I'm just calling it a. I'm just kind of matching those letters, but you could technically call it whatever you want. And so if we were going to write this formula, or this sequence recursively, my a1, my first term is 3. And then the pattern is we take, for every term, we look at the previous term. So a of n is a of n minus 1. So a of 5 is equal to a of 4. And then we're going to do some operation. In this case, we're multiplying by our ratio. Our ratio in this case is 2. So we're multiplying by 2. Well, I don't know a of 4. That's kind of annoying. So I'd have to figure out what a of 3 was, which means I'd have to figure out a of 2, and so on. The only one I can really figure out right away is a of 2. A of 2 is equal to a of 1 times 2. So 3 times 2 gives us that 6. And then a of 3 now I could figure out once I know the 6. A of 3 would be that. And so there's our recursive definition of that geometric sequence. All right, so then explicit. So this is nice again, kind of like the back, where we don't have to have a particular term. We can figure out any term in the sequence this way. If I wanted to know, what is the 50th term in this sequence? It's a really big number, by the way. We can plug it straight into an explicit formula. So we can define a of n is equal to, it's whatever our starting number was. So in this case, I'm going to go with this a that we started with, our starting term. And then before it was plus some number of differences. Well, now it's times r's. Every time we're multiplying by another r. So we're multiplying by r, and we're multiplying by another r. The way that we show that is with an exponent. And we're multiplying by some number of r's. The number of r's is, so in the second term we multiplied by 1r, in the third term we multiplied by 2r's, in the fourth term we multiplied by 3r's. So it's always the term number minus 1. So that's how many r's we're multiplying by. And that gives us our term on any number. We can plug in an n and we multiply by some number of r's, and that gives us what that term is. All right, so down here to an actual example, I started with 3. So I guess I went with a again for this one. A of n is equal to whatever my starting number is, so that is 3, times my ratio, which my ratio here, I'm multiplying by 2's, or I could see it right there, my r as well. We're multiplying by 2 to the n minus 1. That's how many r's we multiplied by. So for my second term, I multiplied by 1, 2, right? So if I plug in 2 there, 2 minus 1 is 1, and so I add 2 to the first power is just 2, and I just multiply 3 by 1, 2. But for my third term, right, so that's how we get 6, my third term, we would multiply by 2 2's, 2 squared, which is 4. 4 times 3 is 12, and there's my third term. And then my fourth term, it's 3 of those. 2 cubed is 8, so 2 times 2 times 2. We've multiplied by 2 3 times. 3 times 8 is 24. All right, and so if I want to figure out what a term is that's a long way from here, we could try and do that. I don't even know if we can do this. All right, say I want to know my 50th term. Well, I would raise 2 to the 49th power, which, let's see if I can do that. 2 to the 49th. Ooh, holy moly. All right, and then I need to multiply that by 3 more to figure out what the number is. So if I multiply that by 3 more, all right, I don't even quite know what that number is, but it's really big. I know that much. So yeah, this is growing a bit faster than before. Well, this because what the pattern is here is this is exponential growth. We see that this is doubling every time. Exponential growth, we know, is very fast. It gets very big very fast. That's why the coronavirus that's going on right now is so scary, is because it's growing exponentially, and so in time, hopefully it's not doubling every whatever with that rate. That's an extreme rate, but it does eventually start to grow faster and faster and faster, unless we can change that ratio that's going on. That's kind of our goal. That's why we're all staying home, is so that we can make that rate of growth as small as possible, and then eventually, hopefully, we can kind of curve out and have that logistic growth. All right, so there we go. There's our 3 different definitions. Well, let's look at it starting in a couple of different points. What if we start from the recursive formula? Well, my first term is 8, and then each term after that, I look at the previous term times 1/2. That's my ratio here. I'm multiplying by 1/2, or effectively dividing by 2. And so we can do 8 times 1/2. So like my second term, c of 2, is equal to c of 2 minus 1. So c of 1 times 1/2, that previous one times 1/2, which is 4. And then c of 3, my third term would be c of 2, so 3 minus 1 is 2. So the previous term, which is 4, times 1/2, and we get 2. And then we get 1, and then we get 1/2, and then we get 1/4, and we continue on forever. And so that's actually, because that ratio is 1/2, we actually see it decaying. That's exponential decay, is that pattern that's going on here. And then if we want to write the explicit formula, so c of n, so I'm going with c's here, is going to be, we're going to start with our starting amount, 8, and we're going to multiply by a bunch of 1/2s. So times 1/2, I'm going to put that in parentheses so we're clear, 1/2 to the, and how many 1/2s am I multiplying by? Well, it's always actually going to be, if we're doing this format of it, n minus 1. So it is, at first I didn't multiply by any 1/2s, but the second term I multiplied by 1/2, 1/1/2. And by the time I get to the third term, right, I'm multiplying by 2 1/2s. And I guess I'll throw that in parentheses as well to to make sure it's all perfectly clear, but I think that was obvious. All right, so there we go. There's writing that recursive formula in the explicit. And finally, what if we start explicit? Well, my starting amount here is 1, and I'm multiplying by some number of -3s. -3 is our multiplier here. And that's a bit weird in terms of exponential growth decay. Negatives, we'll see it bounces up and down, and we've not really graphed that, and it's weird to have a negative base for those ones. So, but we can still do this all right for our sequence. So if I plug in 1, the first term, so 1 minus 1 is, to get the first term, d of 1. So we have 0 for that exponent. -3 to the 0 power is 1. 1 times 1 is 1. So my first term is 1. And that should always be the case. You should always get 0 as that exponent when you plug in for the first term. Then the second term, I can plug in 2 for n. 2 minus 1 is 1, so I'm going to do -3 to the first power, which is just -3, and -3 times 1 is -3, so I've multiplied by -3 one time, and I'm there. All right, and then we can plug in the third term, and that would be, I would square -3. Well, that's times 9, or -3 squared is 9, and positive 9, right? So even powers give us positive numbers. So this sum's going to be jumping back and forth. So I got positive 9 times 1 is just positive 9. And then my next term, and so we can kind of see the pattern from we're multiplying by -3. -3 to the, so this is my fourth term, and we could plug in 4 there and cube -3, get -27. Or I could just realize here, I'm multiplying by -3, I get -27, and then another number, so I'll hit ... all right, so there's our going from explicit to there, and then our recursive formula, we could do d of 1, so our first term is 1, and then from that point on, d of n is equal to d of n minus 1, the previous term, and our pattern is we're multiplying by -3s. That's our ratio here. And so there we are. We can define that recursively as well. So hopefully you're feeling all right, switching back and forth between geometric and arithmetic sequences and just the sequence version, the recursive formula, and the explicit formula. Post any questions you have. I'll do my best to answer them. Hope you guys have a good one.